I'm going to start recording. Thank you. So our test 2 is next Monday. I will put up the review tomorrow at some point. Thursday, we'll do nothing new, just go over questions on the review, which you'll already have the answers. So I'll put up the review tomorrow, and I'll put up the answers on either tomorrow or Wednesday, so you have them. It covers all the material in Chapter 3 that we went over. 3.1.3.2 is double integral. Well, 3.1.3.3 are double integrals. 3.1.3 is just a quick intro. And then 3.4.3.3.6. I'm sorry, yes. Oh no. Is that okay? Okay. I'll try it with the microphone this time. All right, so 3.1 to 3.3 are double integrals. 3.4 through 3.6 are the triple integrals. 3.6 is the mass. 3.11 is the surface area. And then the reason 4.1 is underlined is, if you remember, that's all the definitions. And I said you need to know them until we actually use them. So it's sort of on the test, but really just as part of other sections. And then today we'll get into 4.4. 4.2, 4.3, and 4.4 are all line integrals, just 3 ways of doing it. What I'll do next Monday is similar to the quiz, except what I'll probably do is have it so that you can start. So I'll open it up at something like 10:25 or something like that, and then have it open until something like 11:45. Also, it should be a little bit shorter than what they got last semester. That way, if there are technical issues, you'll still have time to figure them out. If they are bigger, you're going to email me and we'll work through it. So don't worry about it too much. If there are technical issues, just send me an email. Assuming you can. So any questions about the test? Actually, I should say, for the tests, you have the page and note things. Well, basically, it's sort of open notes, but you should still probably write, if you haven't memorized everything, a page of notes, because you try just looking through your notes, then you will not have time. So making it so that even though you should have time if there are technical issues, if you're going through all your notes for each question, you're probably not going to have time to finish it. So it's sort of open notes, but really you want to write up something so you have it in one place. But any questions on the test? Okay. So let me start with what is on the end of last notes. If you looked at my written notes, since I forgot to record. And I think we partially did this, but we can start it again anyway. Okay, so here is a vector function, or force field, or whatever we're looking at. And so we haven't made a mistake. let's show it's conservative, and then we'll find the potential function, which remember is similar to the antiderivative. So what we found, what I said, and I don't think I actually did it, or maybe I did, is it is conservative if all the second order derivatives work out. So there are two ways of doing it. One way is I can look at the curl and this is really just a notation for remembering how it works. And for the test, it's probably not a bad idea to just remember that this is just a way of memorizing this. And that last one is if you have two dimensions, two variables, that is the two-dimensional curl. So conservative means that there's a function whose gradient is equal to it, and that happens to be true if this vector is equal to 0, which is equivalent to, if you remember in two variables, what we did is we just said, well, all the mixed second derivatives have to be equal. And so here that's still true, so you can also do it that way. So for example, the first entry would be the derivative with respect to x. So if I take the derivative of the first one with respect to y, I should be getting the same thing as if I take the derivative of q with respect to x, which is that last term. If I take the derivative of p with respect to z, I should get the same thing as if I take r with respect to x, which is the middle one. And if I take the derivative of q with respect to z, I should get the same thing as if I take the derivative of r with respect to y. So again, all the mixed ones should be equal. So here, the derivative of r with respect to y is, and you can see I made all these fairly easy ones, derivative of r with respect to x is what? And since I'm telling you to show it's conservative, it hopefully is that the derivative of q with respect to z is also x, which it is. Derivative of p with respect to z is, and again, hopefully I've been messed up, the derivative of r with respect to x is, again, y. Derivative of q with respect to x is 6x plus z. And the derivative of p with respect to y is, again, 6x plus z. So since that is the zero vector, it is conservative. So in some ways, the curl will come up later. I think we get to it. So we might use it as something for itself. But for now, you can either look at the curl or just look at all the mixed second derivatives. So I think we did something like this on last week, but not for this particular one. So now we want to actually, since we've shown it's conservative, we want to actually get it. And for that, remember what we're doing is we're assuming that p is equal to f of x, q is equal to f of y, and r is equal to f of z, and taking the antiderivatives. So before I erase, any questions on this? Okay. So since it is conservative, f of x, the derivative of that f with respect to x should be equal to that first entry P. And therefore, the function itself should be the antiderivative with respect to x. So we do each one. The antiderivative of 6xy with respect to x is the 3x squared y. Antiderivative of yz with respect to x is xyz. And now any function that only has the variables y and z, sorry about that mess at the beginning, could also be here. In a similar way, derivative with respect to y is equal to the second term. And again, now the function should be equal to the antiderivative of that with respect to y. And we should expect overlaps because, of course, any term that has both x's and y's will have a similar derivative. So antiderivative of 3x squared with respect to y is the 3x squared plus y, which we already have. Antiderivative of xz is, with respect to y is xyz. And now it's saying we might be missing functions just in terms of x and z. But you can see we didn't get anything new. So this second one didn't really get us anything new. We're still saying the function is equal to the 3x squared y plus xyz, but then maybe missing stuff. And finally, the derivative of f with respect to z needs to be equal to the third. So take the antiderivative with respect to z. Again, we start with one we already have. But now we do get something and since each of these are supposed to be the same thing, we should be getting some repetition. So the first one is in the first two. We only write it once. The xyz is in all three of them. And this we get from the third one. And then now we have just a regular plus c, where c is a constant. There is our actual function. And this you can pretty easily double check, which is it should now be that if I take the derivative of that with respect to x, I get p. If I take it with respect to y, I get q. And if I take it with respect to z, I get r. So if you take each of the antiderivatives, don't repeat anything that you get more than once, because you expect that, but take everything that you see in at least one of the three. So this is now the equivalent of an antiderivative, which we'll get to in the next part. But any questions on this? In the text, they do it a little bit differently. So if you look at the text, you can also do it that way, which is what we could have done is after we got to here, what we could have done is taken the derivative with respect to y, set it equal to our f of y, and then find what we're missing. And then once we get that, take the derivative with respect to z, again, equate it to our f of z, and solve for anything that's missing. I find this easier, but whichever way you want to do it is fine. Okay. So now we go into why we care. So part B. Oops, I lost a variable. So that first point is one's, I just rewrite it. Okay. And remember, usually if you go back to the last section, what we would need is a parameterization of the curve going from 1, 0, 1 to 2, 1, 2. But this section says if f, this f, the vector field, is conservative, we don't care what the path is. All we care about are the endpoints. So this is equal to f So we sort of do the equivalent of an antiderivative. So we take the antiderivative of the vector field, we get f from the last part, and then we don't care about the path. All we care about are what is the value at the two endpoints. This is where you're usually checking me. So put the 2, 1, 2 into the function we got in the last one, the 3x squared y plus xyz plus 3z squared. Hopefully 2, 1, 2. And then plug in the other endpoint and subtract. And if it's a closed path, no matter how complicated you make it look, so I go from 1, 0, 1 to 2, 1, 2, and then I go from 2, 1, 2 to 3, 3, 3, and I go from 3, 3, 3 to 1, 1, 1, and then I go from 1, 1, 1 to -1, -2, 5, and then from there I go back to 1, 0, 1. If it's conservative, you don't care about the path because since I'm starting and ending at the same point, I'm going to get 0 because all I care about are the two endpoints. I don't care about what goes on in between. So any questions on this? Okay, so now what I'm going to do is, in some ways, kind of typical. I'm going to ignore homework for now, and I'm going to do another example where we do it the two different ways we have now, and then I'll add a third way, which is the next section. And then Wednesday, we'll mostly just go over examples, although I might quickly introduce the idea of the next section. So what I'm going to do is, for this example, as I said, I'm going to do this in the two ways that we now know, which is the direct way from 4.2, and then the conservative way from 4.3, which is really what you should do this way, 1.4, and then add in a third way. So first let's do the 4.2 method, which is just we parameterize everything, we plug it into the formula. So let's look at C1. So C1 goes from 0, 0 to 2, 0. So what is a parameterization for that? One of them's easy. So we're going from 0, 0 to 2, 0. Y is equal to obviously 0. And x we have a couple options for, and they all work as long as we make them similar. So one way I can do what I said for Thursday, which is what you can always do, which will work out pretty nicely, is use the method from chapter 1, get the vector. So the vector from 0, 0 to 2, 0 is 2, 0. And then the line is xy is equal to the point you start at plus t times the vector. In which case, in this case, you would get x is 2t. And if you do it that way, the nice thing is you're always going from 0 to 1. It doesn't always give you the nicest one, but it will always work if you're doing a line. So therefore, our r of t is equal to the vector function 2t, 0. And here I'm being lazy. I don't actually tell you what we're getting, which is the integral over c. So to do that, in the original way, what we have to do is plug our parameterization into our function. So this one's pretty easy. So 2x, so 2 times 2t, plus y, which is 0, and then x plus 2y, which is again 0. So I just get that. And then I need the derivative of r, which you can see is just 2, 0. I should put this at the top, saying this is what we're actually getting. And then it's a dot product of the two, f of r of t dotted with r prime. So remember, if we're thinking of this as work, this first part is our force. The second part is going a short distance along the line. So usual work, force times distance. And this is equal to, let's see if I can fit it, at squared. Integral of at squared, sorry. Jeez, I can't do anything, sorry about that. In some ways you can ignore this because here we'll find the next one is kind of a pain. So that's 4t squared. 4. Sorry about that. Okay, so that's C1. And now we have to do the same thing for C2. So before I go to the next line, any questions on this? So this is supposed to be an AT. Okay. C2 is going from 2, 0 to 2, 0, 2. What is the parameterization for that going to be? So since circle, we should be using what type of coordinates? Yeah, polar. So and r is equal to 2, so this becomes the 2 cosine of theta. I'll write the more typical t for this, and 2 sine of t. And like the last one, we again do the pieces. Oh, and I forgot one piece, which is t goes from where to where? Obviously 0 and 2. Over 2 because we do the quarter circle. So plug this in. So look at my other notes. So 2x plus y and then x plus 2y. And take derivative. And you see I don't really want to do this one. I lost the dt. I'll room for the dt. Isn't quite as bad as it looks because there is a fair amount of cancellation because when I take the dot product of the first term and the first term, I'm going to get a negative 8 sine times cosine. When I take the dot product with the 2 second terms, I'm going to get a positive 8 sine cosine. So those will cancel, but it's still not great. I get a negative 2 sine, so I'm going to get a minus 4 sine squared of t. And then unfortunately, plus a 4 cosine squared. So if you think about it, it might be reasonable to expect this to be 0 because they're kind of going in opposite paths. As sine increases from 0 to pi over 2, cosine decreases from 0 to pi over 2, and they're kind of symmetric around the middle. So it's not unreasonable to think it's 0, but I would not expect you to be able to do that. So you could leave it like this. And then integral of c would be the sum of those two. So there is 4.2. And for it, you should know parameterizations for basically just lines and circles. So any questions on this? Okay, so let me put back the original function, b. And let me ask, one from 4.3, is this a conservative function? And since it's two-dimensional, this is the easier one. What we need is, if I call this P and Q, I need the mixed second derivatives are equal. So the derivative of P with respect to Y is equal to the derivative of Q with respect to X. Is that true? What's the derivative of P with respect to Y? And derivative of Q with respect to X is also. So it is. So it is conservative. And therefore, we can use the technique from before, which is get the potential function and then just plug in the two endpoints. So like the last one, we'll take the antiderivative of the first one with respect to X. It's two variables, so it'll be a constant in terms of Y. As with the last one, we get some repetition, as you should expect. And we get our potential function is the combination of those two. So any term that is in one or both of our antiderivatives, just don't use any one twice. So let me stop there for a second since this is somewhat new. Questions on how you get this potential function? Okay, so now if I want to get this, then all I have to do is get this potential function, which we just did, and all I care about is the two endpoints. So if I put 0, 2 into this function, I get 4. If I put 0, 0 into this function, I get 0. And there is my integral. So you can see in some ways this is quite easier because we don't care about the path, so we don't have to parameterize anything. Only thing we have to do is take antiderivatives. So, and it's pretty quick, as you can see, to check to see if it is conservative. So not a bad idea to just do it. So any questions on this version? Okay. So since it goes with this, let me add in 4.4, which really is just one case. And then we'll do it using the new case. So let R be a two-dimensional space region. tell you what all the little pieces mean, which is bounded by a simple closed oriented piecewise regular. There's lots of little pieces here. And in this case, just to make it confusing, that's not a partial, that's supposed to be a boundary of R. So with all these little properties, if they are true, then we can change the line integral, so that's a line integral, into a regular double integral. This is supposed to be a py. So the pieces are simple means that, and I'll draw it in the next one, simple means that if I'm drawing it, it doesn't cross over itself. There aren't any places where there are missing pieces. So simple just means I can draw it without lifting my pencil and I don't cross any points. Closed means the usual thing, that it begins and ends at the same place. Oriented says that I'm going in one direction, so I don't go one direction on the path for a bit and then switch again. It's just nice and simple. And piecewise regular again means that I don't have too many corners. So my previous picture where it's a line and then a circle and then a line, that would be okay because on each of the pieces it's regular. So that's the R and dA. The dA is just for either dy dx or dx dy, which we'll see once we do an example. So in some ways, the usual thing, this is the presentation. Now we're going to go back and actually use it. So hopefully once we use it, it'll be more obvious what's going on. So let me go back to the example. So part C. So again, we have the function, we have the space, and what I'm going to do is let me add in this extra piece. And now at this point, with the added C3, we can use this new theorem. Because now if you look at it, it's a closed path. It's simple in the sense that there's no crossing over. There are lines and circles, those are regular, so we don't have to worry about that. And now this is our R, whereas the C1 plus C2 plus C3 is that boundary of R. So we call it C prime. In the theorem, it's this. And so it says, I can now look at this two-dimensional curl, and I can do that integral of that function over R. So here, obviously, I made this easy. Q of x is equal to so I made this really easy. I think more than I meant to, but that's okay. Actually, no, I had to for do all pieces. C1 plus C2 plus C3 is equal to, that's supposed to be boundary R. Sorry about that. So that symbol in front of the R is supposed to be a little boundary symbol. You'll see we don't really, it doesn't really come up, so don't worry about it too much. So, as I said here, because of for it to work with B also, this has to turn out to be really simple, because since it's conservative, the integral over this full path, the C prime, it's got to be 0. So Q of x here is 1, P of y is 1, this is equal to 0. So the Green's theorem says that the integral of C prime of f dr is equal to the double integral over r of this function, and I'm going to leave it like this because I don't really want to put in the 0, and dA. So let's set it up even though we know this is going to be 0. And the idea is now this is like the double integrals we started with in chapter 3, which I want to integrate this function over r. So I do the bottom to the top. And since it's a circle, I would probably do it in polar coordinates. So I go from 0 to 2, and 0 to pi over 2, 0, and then r dr d theta. The idea is I can change it from a line integral to an integral such as we saw in 3.2 or 3.3, when I can either do with regular coordinates or polar coordinates. Here, obviously, I don't have to do anything because it's 0, so the whole thing is 0, but just to show how I would set it up. And obviously, we're going to have to do another one, but so Green's theorem says we can change a line integral into a double integral over a region, as long as it's a closed space. Okay. So if you think about it, we aren't really done because the original one isn't closed. So the idea is I can still use Green's theorem, which is on C prime, this is the integral 0. And C prime is equal to the original C, which was C1 plus C2 plus C3. So what we could do is, if I was going to use Green's theorem for this, is I would close it with C3, use Green's theorem to make it as a double integral. And now I have to go back and get what is it on C3. And for that, I would probably use the method from part A. And so I parameterize C3, where on C3, x is equal to 0, and y might be something like 2 minus 2t from 0 to 1. So I might as well, since it's fairly quick. So first, before I do this, I'm going to do another example, but any questions on this setup? So again, I am going from 2, 0 to 0, 2, to 0, 0. So I make it something like that. I plug in, it's 2x plus y, x plus 2y. So put the the x and y into the function we have. Take the derivative. Oops, I really need to put the whole thing in. Get that? And we better get the same number. So Green's theorem works if it's closed, but if it's close to closed, then it might make sense to add an extra term, deal with that separately, and then use Green's theorem. So we now have 3 methods for doing line integrals. So any questions on this part before I do another example? Okay. Sorry about that. Not sure how I did that. So here's our C. And so therefore, this is our R. You can see it's a closed path. So the first thing you might want to look at is, thank you, is check to see if it's conservative, because if it's conservative, this is really easy since it's a closed path. The line integral will be 0. So preliminary question, is f conservative? Doing well. So is this conservative? So we need to look at the two-dimensional curl. So we need to see if p of y is equal to q of x. Is that true? What's the derivative of p with respect to y? Right, so no, because the derivative of p with respect to y is equal to 1 is not equal to the derivative of q with respect to x. So it's not conservative, which means I can't use in some ways the simpler thing, which is I wouldn't even have to find the potential function in this case because it's closed, and so the integral is 0. So if that was x plus sine of y, this would be a really simple problem. On the other hand, it is closed already, which means we can use Green's theorem, in which case I want q of x minus p of y, and then the line integral becomes the double integral over r of this q of x minus p of y dA. In some ways, this is a typical type of thing for tests and finals where you want to use Green's theorem, because if I integrate a constant over a region, what do I get? So I can pull out the 2. If I integrate 1 over a region, what do I get? The area of the region. So this one is a triangle. So I don't have to do an integral at all. I can just do 2 times the area. Well, the area of this thing is it's a triangle. So it's that 1/2 base times height. So it's 1/2. So 2 times 1/2 times 3 times 2. And I get it 6. So this is kind of, as I said, typical test final one, because if you tried it using the base one, it's a pain because you'd have to parameterize the 3 lines. And you can see these extra pieces, the ex and sine of y, are going to make it a pain to actually do the integral. On the other hand, with Green's theorem, it's been designed so q of x minus p of y is simple. And so it ends up being simple using Green's theorem. Right. So as I said, these 3 sections go together. So 4.2, 4.3, 4.4 are all line integrals. 4.2 is the base way of doing it, which is you parameterize and use the formula. 2 is if it's conservative, you only care about the endpoints. So you get the potential function and then plug in the endpoints. And Green's theorem says if I have a closed curve, I can make it into a regular double integral as opposed to a line integral. And I'm mostly going to stop here. Let me just say that the next thing we do is we start doing flux, which is things such as I have a river. I have the equivalent of a net across the river, and I want to say how much water goes through that 2-dimensional net. So kind of the next level, instead of work around a line, we're going to look at flow through a 2-dimensional object. But we might start that Wednesday, but it's not going to be nearly enough to put it on the test. So let me stop here for today. So any questions on this? Also, obviously, we're going to have to do some examples. So kind of what happens a lot for us. Wednesday, most of the class will be doing examples from 4.2, 4.3, and 4.4. So if you haven't already, start working through those, and we'll do at least a few of each. Okay. So again, let me ask if there are any questions, because then if not, do the usual thing, which is I'll stop recording, and then if you have questions, you'll stick around. So any questions? Okay. Also, reminder, test is next Monday. Review will be up sometime tomorrow. Okay, so I'm going to stop recording.